Alright, so let's talk about normal stress. So previously, again, we've been talking about stress and strain, how they relate, so on and so forth. After all the discussion about how to figure out what loads are applied to structures, we need to figure out how those structures get stress induced in them. So we're going to be delving deeper into axial loads and how they induce stress. And then we've been talking about how to figure out how to find support reactions using your equilibrium equations, and we mentioned indeterminate problems. So problems where we don't necessarily know enough information about the system in order to be able to calculate what the reactions are just based on the equilibrium. Well, thankfully, there's ways to go about that don't rely upon that. So we'll talk about a few of those. And we'll be talking about thermal effects, and we'll be talking about stress concentrations. So to start off, we've got the Saint-Venant principle. So the idea is that we're using stress to measure basically the force distribution. So how concentrated that force is on a certain cross-section, and then strain's being used to measure how it deforms when stress is applied to it. Or you could look at it vice versa. If I'm pulling on a thing a certain amount, like if I'm stretching it a certain amount, if I'm applying a certain strain, how much stress is caused by that. You can look at it in both ways, really. But if we're still in a linear elastic regime, then Hooke's law applies. So we got a proportional relationship between the two based upon our Young's modulus, or shear modulus. We're talking shear, but anyways, we're not talking shear this lecture. This lecture is on normal stress. But thus far we've been talking about average stresses. So the actual stress distribution is not necessarily evenly distributed. So it depends upon the geometry, and especially it kind of depends upon how the geometry changes. If you have any abrupt changes in the geometry of your object, then essentially the stress kind of needs to get distributed around those disruptions, and it causes stress concentrations. The loading matters, and kind of where upon the member we're looking matters. For example, if we have this bar, if it's fixed at the bottom there, and then we've got a load at the top, then say a load applied through a hole at one end. So if we've drawn these grid lines on the bar, and then apply this load, kind of how the grid lines distort will kind of show us this localized deformation. So you can kind of see in this example here, you're going to get non-uniform deformation at either end of the bar. So it's a bit more extreme at the end with the hole in it, and that's just because at the end the entirety of the load is concentrated on that hole. So you're going to get more of an extreme stress concentration going on, whereas at the bottom there's still going to be some localized distortion. And that there is essentially due to the fact that since the bar is fixed at the bottom, it can't contract due to the Poisson's ratio effect. So it's gonna essentially, as we stretch it out axially, it's going to want to stretch in the lateral directions, but it's not going to be able to due to the fact it's bonded to that surface. So as a result, it's essentially you're going to have some distortion at that end. So at either end, you're going to get some non-uniform deformation. But what does happen is that in the middle, the deformation evens out, and then in between, you get uniform deformation through the midsection of the bar. So, and kind of how concentrated or how non-uniform that distribution is kind of depends upon how far away from the thing causing the non-uniformity is. So if you're further away from where the external loads are applied, then it's more uniform. So generally speaking, you can kind of assume uniformity if you're at least as far away from the load as the largest dimension of the cross-section. So if your cross-section is, say, 10 millimeters by 50 millimeters, as long as you're 50 millimeters away lengthwise from the load, then you can usually assume that you're going to be fairly, if not completely, uniform. So yeah, this effect was first noticed by French scientists Adhémar Jean-Claude Barre de Saint-Venant in 1855. So yeah, the gist of it is kind of what we talked about: the stress and strain produced at a point in a body, as long as you're sufficiently removed from the from the region where the load's applied, then it'll be the same as if then the stress and strain produced by any applied loading will have the same result as if applied to the body within the same region. So essentially, basically, that's basically just saying everything averages out in the middle. Also, to a degree, we can, to a degree, this will also affect with a changing cross section. As long as you have a sufficiently gradual change of your cross section, then essentially you're going to have an ability for the stress to even out as it goes along. So you can have gradual, like if you have a gradual increase of the cross section as you go along, then the stress will have a chance to spread out gradually. So you can kind of assume that as a result, at any particular cross section, the stress can be relatively evenly distributed based upon that. Whereas if you have really abrupt cross section changes, then that wouldn't necessarily be the case. So if you have a bar that's doing this, then that's fine. If you have a bar that's doing this, then essentially, like, you're gonna have load lines kind of represent the path the stress taken, and when you get to this really sudden cross-sectional change, they're not going to have a chance to kind of evenly distribute it. So they're still going to be more concentrated in the center than they are at these edges, because it's kind of spreading out too fast. But anyways, what we can do is, based upon what we do know with Hooke's law and the basic definition of stress and strain, we can figure out an equation that relates how much stretching you're going to get as a member is subjected to axial load. So we've got this bar here. It's got some sort of cross-sectional change. It's got a cross section that we can define based upon its position, based upon the x position. We got a load applied to it. P1 equals P2, obviously, since we're in equilibrium here. Actually, wait, no. P1. Sorry. I'm jumping the gun here. We got loads applied to it, and that load might vary because there may be some distributed load applied to it. But at the end of the day, we're going to get some sort of stretching here, some sort of stretch delta. So if we look at a particular, at a tiny little slice, a differential element of that, then when we zoom in on that, we're going to get P as a function of x. So the load is a function of x based upon what this load is and then what distributed load occurred in the meantime. We're going to get an area as a function of x. And again, it could be as simple as we've got a cone of some sort, or what have you. And that's going to cause, essentially, this tiny little slice to increase its length another tiny little bit. So based upon so we've got this equilibrium situation going on. We've got this little bit of stretching here. So we know that our stress is just going to be the load at that cross-section divided by the area at that cross-section. And then we got our strain here. So strain is always just the stretching divided by the original length. So our d delta over our dx. So again, we just relate this to Hooke's law, assuming we're in the linear region. So stress is just going to be equal to Young's modulus times our strain. So we can just go ahead and relate these two. So the P of the P of x over A of x is going to be equal to E times our d delta over dx. Or put another way, we can find what our d delta is here in terms of dx times these parameters. And then if we want to get the total elongation, now we just integrate that. So integrate that over the length of the bar, and we get our total elongation. So that'll tell us how much this bar is going to stretch based upon this loading overall. And then if we have a constant load and a constant cross-sectional area, then it's a relatively simple calculation there. And again, you may have distributed loads that could be changing your P. You could have a varying cross-section that changes your A. Oftentimes, you don't necessarily have distributed loads, but you have, say, certain point loads that will cause that will cause you to have they'll allow you to break your bar up into several segments with either different axial loads or different cross sections, or perhaps both. But essentially, you can figure out what's going on there just by kind of breaking that bar up into segments, figuring out how much deformation you get in each segment, and then adding that up over the bar. So again, sign convention shouldn't be too surprising. We're following what we've been following all along. Tension is positive, elongation is positive. So again, regardless of the coordinate system chosen. So if we're increasing in x here versus increasing in x here, both of these are going to be positive internal forces, positive internal axial loads and axial stresses, because they're causing tension and they're causing elongation. Whereas pushing on the bar in this direction or pushing on this bar in this direction causes compression and contraction, so those are both negative internal axial loads, negative axial stresses, and negative displacement. So let's work through an example here real quick. So let's start off with what we always start off with a free body diagram of this bar here. So we've got okay, so I'm going to have a reaction dx here. I'm going to go ahead and take got this 8 kips that is going on there. I'm just going to combine those. It's on either side. We can combine them into a resultant. In the middle, that's 16 kips. We can do the same thing with 4 kip into 8 kip. And then we're pulling upwards here with 15 kips. So, simple enough to solve for dy. The sum of the forces in the y is going to be equal to 0. So we got 15 minus 8 minus 16. Those are all kips. Plus dy is equal to 0. Okay, so what do we get there? Moving the other ones over to the side, 16 plus 8 minus 15 gives us 9 kips for dy. dy is equal to 9 kips. So we can figure out what the internal load is in the different sections here. So essentially, we know that in this, if we take a slice of any point in this little top section here and do a free body diagram of it, it'll be plus 15 kips, which means that the internal stress there needs to be based upon 15 kips as well. So from here to here, we got a 15 kip load. It's going to be tensile, so it's positive. If we take a little slice here, then the internal load's going to be based upon 15 up, and 8 down, and then whatever reaction we have there. So that reaction there is just going to be based upon the 15 minus the 8, since they're acting in opposite direction there, which means that the internal load there needs to be 7 kips. So again, that's still a positive one, because the 15 that's pulling up is more than the 8 that's pushing down. So overall, you're still pulling upwards on that section there. So 7 kips. And then if we take a little slice here, and draw a little collar there. Now we got 15 up, got 8 down, and we've got another 16 down, which means that we're getting to 9 kips, obviously, but essentially the 9 kips is going to be pushing upwards in this section. So from here to here, we're in compression. So that's going to be a negative 9 kips. So essentially what we can do is we can essentially we can break this up into three different sections because we got three distinct areas. We got the one combination of the 15 kip tensile and the smaller cross section. Got the larger cross section and the 7 kip tensile, and then we have the 9 kip section compressive and the larger cross section. So three distinct sections that we can find the total displacement for. So we'll call that a displacement from A to D. So that is just going to be the sum of the sum of the displacement for the individual sections. So again, the displacement in those individual sections is just going to be equal to the load times the length divided by the cross-sectional area times the E section. So if we break it up into the three sections, the one constant we have there is the E. So we can just the 1 over E here, and then split it up into kind of the PL over A terms for each of these. So the P term for the first section here, that's going to be 15,000 pounds times the L, which is for that section 2 feet. It's a 2-foot section. I'm going to put that as 24 inches. And then the cross-sectional area for that point is 1 inch squared divided by 1 inch squared. The next section there, the section with the 7 kip tensile load, so 7,000 pounds times the it was 1.5 foot section, so 18 inches divided by 2 inches squared is that cross section. And then the next one we've got here is the minus 9,000, the minus 9 kip load. So plus, and it's a minus 9,000 pounds. It's a 1 foot section, so 12 inches divided by 2 inches squared. And then for all that, we're also going to need to know what E is. So we were told that it was an A737 steel. So we just need to go to the table at the back of Hibbler's, and we can find out that we've got a modulus of elasticity that's 29 times 10 to the 3 KSI. So what I'm going to do here, I'm going to actually put that as 29 times 10 to the 6 PSI, because I don't want to have to deal with times 10 to the 3 KSI. That just sounds silly to me. But anyways, I need to take these terms, sum them up. So we got 15,000 times 24 divided by 1 plus 7,000 times 18 divided by 2 minus 9,000 times 12 divided by 2 gives us 369,000. So the units there, they'll be pounds, inches divided by inches squared. So that'll be pounds per inch. And then multiply that out by the 1 over PSI, the 1 over E. 29 times 10 to the 6 pounds per square inch. So the pounds cancel out here. One of the inches cancels out. So we're left with inches as our end result, which is what we're expecting. We're expecting to get some sort of elongation, so we expect that to be in terms of inches, or in some unit length at least. So if we kept these terms here in feet, the length terms in feet, then obviously we'd have feet there as well. So anyways, 369,000 divided by 29 times 10 to the 6 gives us a total elongation from A to D, which is going to be equal to 0.0127 inches. So there. That's our total stretching. Well, really, that's the total combination of the stretching in these two segments minus the contraction in this segment, because that one's going to be getting smaller. These ones are going to be getting longer, and this will be the net effect of those two.